Alright, so here's question 1. Evaluate the limit as x goes to pi over 2 of x minus pi over 2 times tangent of x. And notice, this goes to 0, this goes to infinity. There are a variety of ways to attack this. Have at you. Okay, so there's one more indeterminate form that we're going to consider, which are indeterminate exponents. And these are when I have a limit that looks like 1 to the infinity, infinity to the 0, or 0 to the 0. Why are these indeterminate? Well, when I have something going approaching 1 to the infinity, that means that the base, what is being raised to the power, is approaching 1. And 1 to anything is 1. Except if I have a power infinity, that's actually trying to pull it away from 1. If my base is approaching 1 from above, then the infinity power is trying to pull it off to infinity. Whereas if my base is approaching 1 from below, the infinity power is trying to pull it down to 0. So this infinite power is really trying to pull us away from 1, whereas the base is trying to pull us towards 1. Also infinity to the 0. Well, anything to the 0 is equal to 1, right? Well, if I have an exponent that's approaching 0, that's going to try to pull the limit down to 1. But if the base is going to infinity, that's trying to get off to infinity. So this thing is, being sort of stretched between infinity and 1. Similarly here, 0 to 0. As the base is approaching 0, it's trying to pull the limit down to 0, but the exponent 0 is trying to pull it up to 1. So there's a fight over there. Now what do we do to transform one of these exponential and determinate forms into something where we can apply L'Hopital? Well, what we do is we take natural logs. That's often how we have dealt with exponentiating functions, is we take logs to turn it into a product. So if L is the limit as x approaches c of f of x to the g of x, and it looks like one of these three things, then we'll take natural logs. Due to continuity of the natural logarithm, the natural log of L will be the limit as x goes to c of the natural log of f to the g. And I can pull the g out, so I have the limit as x goes to c of g times the natural log of f. You can check that for each of these three sorts of indeterminate products. This turns into infinity times 0 or 0 times infinity, and then we can use our, any of these indeterminate exponents will turn into an indeterminate product down here. All right, so let's do an example. Let's take the limit as x goes to infinity of 1 plus 1 over x raised to the x power. Now this is of the form 1 to the infinity. 1 over x goes to 0 as x goes to infinity, so the inside is going to 1. It's trying to bring the limit closer and closer to 1. However, this power x is going to infinity, so this is of the form 1 to infinity. So the base is trying to get closer and closer to 1, but this x is getting bigger and bigger and bigger, and is multiplying this 1 plus 1 over x against itself a lot of times, and is trying to make it large, since 1 plus 1 over x is bigger than 1. Okay, so let's let L be this limit. Then the natural log of L is the limit as x goes to infinity of the natural log of 1 plus 1 over x raised to the x power. So then I can bring out the x power, and I get the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. This is now the form infinity times 0. X is approaching infinity, and 1 plus 1 over x is going to 1, so log of that is going to 0. So now I need to transform this into a quotient. Do I want to put the x in the denominator or the log in the denominator? You want to put the x in the denominator. Putting the log in there would be crazy. So, anyways, I put the x into the denominator as x to the minus 1. I'm also, just for the sake of making my work a little nicer, I'm going to rewrite 1 over x as x to the minus 1 inside of the log. So now this is of the form 0 over 0. We already saw this is going to 0, and as x goes to infinity, x to a negative exponent goes to 0. So now I can apply L'Hopital's rule. The derivative of the top, according to the logarithmic derivative, is negative x to the minus 2 over 1 plus x to the negative 1. The derivative of the bottom is negative x to the minus 2. So my negative x to the minus 2's cancel out, and I'm left with 1 over 1 plus x to the minus 1. Now I can plug in x, because x to a negative exponent goes to 0 as x goes to infinity. So I get 1 over 1 plus 0, which is 1. Now I'm not done when I do one of these exponential types. What I evaluated was not the limit L, I evaluated the log of the limit L. So since the natural log of L is 1, L is e to the 1, or just e. So the limit of this expression is e. In fact, this is one of the definitions of the number e. This thing. Let's do one more example of an exponential indeterminate form. Now, it's actually kind of hard to come up with sort of natural examples where the behavior sort of isn't similar to the one that we just looked at before. So what I came up with is this. Let's look at the limit as x goes to infinity of 1 plus e to the x raised to the 1 over log of x power. It's a really weird function. You probably will never run into it, but it's a good example of an indeterminate form. Now this has form infinity to the 0. As x goes to infinity, e to the x goes to infinity. If I add 1 to that, it's still going to infinity. Now as x goes to infinity, log of x goes to infinity, so 1 over log of x goes to 0, so this is infinity to the 0. So let's call the limit L. Because it's an exponential form, I have to take the natural log. So the natural log of L is the limit as x goes to infinity of the natural log of 1 plus e to the x raised to the 1 over natural log of x. That becomes, bringing the exponent out, the limit as x goes to infinity of 1 over natural log of x times the natural log of 1 plus e to the x. And that's equal to the natural log of e to the x plus 1 over the natural log of x. Now this is infinity over infinity because, well, e to the x plus 1 is bigger than e to the x, and log of e to the x is x, so this quantity here is bigger than x and it goes to infinity, and log of x goes to infinity. So I can apply L'Hopital now. This one, it really naturally set itself up into a quotient. I didn't really have to think about the fact that this was a product and turn it into a quotient. It just very naturally turned into a quotient. So I apply L'Hopital's rule. The logarithmic derivative of this is e to the x over e to the x plus 1, the derivative of the inside over the inside. The derivative of log of x is 1 over x, so I have e to the x over e to the x plus 1 all over 1 over x. I multiply by the reciprocal of the bottom to get x e to the x over e to the x plus 1. Now here there are a variety of ways to attack this. I could divide the top and bottom by e to the x, because that'll give me x over 1 plus 1 over e to the x, and you can show that goes to infinity. But we can also apply L'Hopital's rule again, because this is infinity over infinity. X is going to infinity, so x times e to the x, which is also going to infinity, goes to infinity. The bottom we already talked about going to infinity. So applying L'Hopital again, the top, due to the product rule, becomes e to the x plus x e to the x. The bottom becomes e to the x. Now I've got a common factor of e to the x. I'm left with the limit as x goes to infinity of 1 plus x, and that is infinity. So the limit of the log of L is infinity. Okay, so let's remember, when we compute a limit of an exponential indeterminate form, we generally end up with the log of the limit. Now in the last problem, we got the log of the limit was infinity. What does that mean? What does that mean? Because if L is a number, its natural logarithm is not going to be infinity, it's going to be some number. Well, really, the way we should interpret it is this. If the log of the limit is infinity, then the limit itself is infinity. So whenever you do an exponential indeterminate form and end up with the log of the limit being infinity, the limit is infinity. The other scenario you could run into that is a little problematic is if the log of the limit is negative infinity, but in that case, it turns out that the limit is 0. L is 0.